Hi, the topic for this video is going to be BST, that is binary search tree. Before diving into the theory of BST, we are going to spend just a little bit of time on understanding how arrays work behind the scenes. So arrays are basically a collection of some sort of data type, a homogeneous data type, which reside in contiguous memory locations. Well, they may not actually be in contiguous memory locations in terms of physical memory addresses, but for all practical purposes of writing code around arrays, we can assume that they are in contiguous memory locations. The actual memory allocation for an array would be different for different OS or different architectures. So let's take an example. Let's say that we have an array of integers, so it's going to look something like this. Let's say that we have an array of length is equal to 5. Let's call this array A. Now arrays are indexed from 0. So this is going to be index 0, this is going to be index 1, this 2, 3, and this one will be 4. Let's say that we have elements here 2, 9, 8, 3, 8. Now the lookup from arrays is constant time. So you can say something like array at index 3, or which would basically means the fourth element in the array, which is the element present at index 3. Its value will be 3. This 3 is coming from here. Okay, now this is a constant time operation. By that what I mean is that it's not dependent on the length of the array. So even if we had an array of length 1 lakh, even in that case, if we were to get something by index, let's say array of 523, that is the element at index 523 in this array of length 1 lakh, this would still be a constant time operation. This would take exactly the same amount of time which would take to query an array of, let's say, only 10 elements, and we were querying an element at index 5. So this lookup operation is independent of the length of the array. That's why it's big O of 1. It's not big O of n, it's big O of 1. It's constant time operation. Why can we do it in constant time is because, as we've already discussed, that arrays, the elements of the array reside in contiguous memory locations. So if we have an array and we are referring it with the name A here, and A is going to maintain the memory address at which it starts. So let's say that the memory address was X. Now let's say that the data type that we are storing is actually consuming 4 bytes in it. Or let's not jump into the numbers. Let's say that the data type is actually taking D units of memory. What this means is that the array at index 0 is going to be at memory address X. The array at index 1 is going to be at memory address X plus D. Okay, the array at index 4 would start from a memory address that will be equal to X plus 4 times D. Okay, now this operation, as you can see, is constant time. It's simply one multiplication and then one addition. So it's not going to depend on the length of the array, and once we have the memory location of the desired index, we can simply read from it. That is the benefit of arrays. The problem is that what if we had to find elements from it? What if we had to, let's say, find the position of let's say 3 in this array? In that case, we will have to start from index 0 and we'll have to go till the last index of the array, and we'll have to compare every element with the target value that we're trying to find. Now let's take an example for this. Let's say that this was the array that we had. Three, 2, 9, 8, 7, 6, 10, and we were trying to find what is the index of element 7. So we'll start from I is equal to 0, that is index is equal to 0. We'll check the element at index equal to 0, which we see it's 3. It's not equal to the let's say the target is 7, that is 7 is what we're trying to find out. So 3 is not equal to 7, so we are going to increment the I. We're going to now point I to index 1. We'll check the element present at index 1 with the target, and in this fashion we are going to iterate over the array till we reach the element that we are trying to find. And if we've reached the end of the array and we've still not found the element, then we're going to say that this array does not contain the element that we're trying to find in it. Now this is a linear time operation, because the worst case scenario, if we are starting from index 0, the worst case scenario would be that the element is present at the last index. So in that case, if the array is of length 10, we'll have to make 10 comparisons. If the array is of length 100, we'll have to make 100 comparisons to find the element. So from this we can see that the number of comparisons that we have to make are equal to the length of the array. So this is big O of n. It's of linear time complexity. And if we have to see it visually, if we were to plot a graph, here is the n basically denotes the number of elements in the array, and it's the t, some unit of time, if it goes over the y-axis. Now as the length of the array increases, the find operations time will increase linearly with n. So this will give us a straight line. So this is the linear time complexity, big O of n. Now the problem is that what if we had, let's say, so I'm going to take an example of these many elements. That is, if an array is having 4 billion elements, or you can say that 429 crores 49 lakhs 67,296 elements. That will be equal to 2 raised to the power 32 elements. So this will take over 4 billion comparisons, right? Now, even for the fastest computer, this is going to make a difference. It's going to take significant amount of time. That is the problem. That is where binary search trees come to our rescue. The find operation the find operation on binary search trees is not linear, but it's logarithmic. So what it means is that the if we were to look at the same graph, and if we try to plot a logarithm of n, so it would appear something like this. Now what this means is that if there are 4 billion, almost 4 billion elements in our binary search trees, now this comes with an assumption that our binary search tree is balanced. So if there are 2 raised power 32 elements, then if we were dealing with array, it would take over 4 billion comparisons. But if we were dealing with binary search trees, it would only take 32 comparisons. Now you can imagine the scale at which the difference in the time complexities is. Why 32? Because log of 2 raised to the power 32 to the base 2 is 32. Now this was the mathematical realization of the time complexity. Let's see what a binary search tree actually looks like, and let's try to visualize this insanely good time complexity with the help of a diagram. So binary search trees are something of this sort. Unlike normal trees where root is at the bottom and the branches go upwards, in coding we have the root at the top level, and then we have branches coming out. Now since this is binary, that means that every node in a tree, node is basically this thing, the circles that we have drawn. So every node is going to have at max 2 children. So this node itself can have 2 children. This node can have 2 children, right? So these are the children. Now each of these nodes can further have 2 children actually, not children's. Now for this tree to be actually a BST, it needs to satisfy a particular property. 2 properties we can say. The first one is that every node present in the left subtree, so let's say that we are currently dealing with this node, let's call it R, the root node. So if this is the node in sight right now, then the left subtree of this node is going to be this one, okay, and the right subtree is going to be this one. Now what it means is that what does it require to be a binary search tree is that every node in the left subtree should be less than the value that is present at this particular node, and every node present in the right subtree should have a value larger than or is equal to the value at this particular node. Let's try to see this in action. So let's say that the value here is 50. Here the value is, let's say, 25, and here the value is 75. Here the value is 12. Here the value is 37. Here the value is 6 and 18. Here let's say the values are 30 and 43, let's say, and here the value is 62, and here the value would be 88. Here let's say it's 57. Here it's 70. Here it's 80. Here it is, let's say, 95. So this actually is a binary search tree, because if we take into consideration this node, then we see that all the values, that is 25, 12, 6, 18, 30, 37 and 43, which reside in the left subtree of this particular node, every value in this left subtree is smaller than the value 50. And similarly, every value in the right subtree is larger than or is equal to the value 50. Now this should hold true for every node in the tree. So let's say that we were to have a value of let's say 5 instead of 37 here. Now looking at R, we could see that every node, every value in this left subtree is still less than 50, right? 5 is less than 50 and 5 lies in the left subtree of R. But what about this node? This is in violation of the binary search tree property, because 5 lies in the right subtree of this particular node, the node with value 25, and 5 is smaller than 25. So this is a violation. So every node should satisfy this property, not just the root node. So this was a little bit theory about the binary search tree. Now let's see how the lookups, not actually lookups, but how the find operations take logarithmic time and not linear time. So let's say that we were to find 70 in this tree, right? So if so we are going to always start with root node. We are going to compare the root node's value with the target value that we are trying to find. Let's call it t. Now the node's value, that is 50, is less than the target value, that is 70, or we can say that t in this case is greater than the node dot value, because 70 is greater than 50. Now this immediately gives us a hint, not a hint, but this immediately exactly tells us that 70 cannot lie in the left subtree of this node, because 70 is larger than 50, and we are dealing with the binary search tree. So we can immediately discard this entire left half by just making one comparison. Okay, now the only portion of the tree that we are going to looking into target is this right subtree. So this was step 1, that is comparing it with this thing. Now we are going to compare 70 with this value. 70, you can see, is less than 75, so we can discard the right subtree of 75. Now again we see that out of the remaining elements after first comparison, we are discarding half of the elements just by making one more comparison, right? Now we've determined that 70 is going to reside in the left subtree of this node. So we're going to compare 70 with this node 62. 70 is larger than 62, so we are again going to discard half of the remaining elements. We are going to discard the left subtree of 62. We are only going to check the right subtree. Now we here see that 70 is equal to the node value that we are currently looking at, so we are going to say that yes, we found 70, or we are going to return the position of this particular node. And if we have encountered a node which does not have any children, or the children, that is the right and left, are both null, and this current node's value is not equal to the target value that we are trying to find, we can say that this binary search tree does not have the value 70. So here we can see that we only had to look or we only had to make 1, 2, 3 and 4 comparisons to look to find 70 in a tree with size of 1 2 3 4 5 6 7 8 8 and 7, that is 15, right? So this is like a dry run kind of thing to actually see that why the find operation takes logarithm time and not linear time. Now, how these arrays are going to be represented in code, we are going to use a normal array only, but we are going to do operations as if we are doing it with binary search tree. So assuming that we have an array, let's go to a new slide and let's see how we're going to represent it in an array. So here was our tree. This is the root node. Then it had two child. Then each of them had two children of themselves, and then finally they had children, two each. Now this is the total of 15 elements, right? So we can create an array of length 15, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. Okay, so if we were to put this root node at index 0, if we were to traverse it something like this, let me take a different colored pen. Let's say that the traversal is going to be something like this, that is one level after the other, right? So in this traversal we see that this is the first node that we encounter, so this is going to be at index 0, right? So its index is going to be 0 in this array that we are going to use to store our binary search tree. The next node encountered in this path was this one, so it's going to stay at index 1. Then this one is at index 2, then 3 4 5 6 7 8 9 10 11 12 13, and lastly this is going to reside at index 14, that is this one. And if we were to label the array, it would be 1 0 1 2 3 4 5 6 7 8 9 10 11 12 13 and 14. Now if we try to find a pattern here, we can see that given let's say I, that is given the index of a particular node, we can determine its children nodes indexes in constant time. That will be 2i plus 1 and 2i plus 2. So let's take this node. So its index was 2, that is I here was 2, and 2 times 2 plus 1 would be 5, and 2 times 2 plus 2 would be 6. And we can see from this diagram that left child of this 2 is 5, at index 5, and the right subchild is at index 6. So this logic allows us to represent a binary search tree in linear array and still achieve logarithmic time complexities. Now let's see a drawback of binary search trees. So let's say that we have some elements and we want to the first step would always be to construct a binary search tree from given elements and then perform lookup operations, search operations basically, in logarithmic time. So if let's say the elements are 20, 10, 30, so this would be the first element would be the root node, then we are going to insert 10 in it, right? So 10 definitely cannot go towards the right of 20 because it's a binary search tree, so 10 will be the left child of 20. Then 30 will go to the right side of 20 because for every insertion we are going to start looking from the root node. Then let's say the next element that we are inserting is 5, the next element that we're inserting is, let's say, 15, then we are inserting 25, and then we're inserting 35. So if we are inserting 5, we'll compare it with 20. 5 is less than 20, so we'll move towards the left tree, left child of 20. 5 is again less than 10, so it will have to move towards the left child of 10, which currently is null, so we'll put 5 here. When inserting 15, we'll have to move towards the left subtree of 20, because 15 is less than 20, but after comparing 15 with 10, we see that 15 is going to reside in the right subtree of 10, and currently the right subtree of 10 is null. There is no right subtree, so we're going to say that 15 is the right child of 10. Similarly, 25 will go here, because 25, after comparing to 25, we see that it's going to reside in the right subtree. After comparing 25 with 30, we see that it's going to go in the left subtree of 30. So 25 comes here and 35 is going to come here. So this is how we construct a binary search tree. Now, even while construction of binary search tree, we have to deal with n elements, right? Given that n is the total number of elements. Also, for insertion, we can see that insertion is kind of like lookup only. We have to find at which location we need to put this new element at. So the time complexity of inserting an element into a binary search tree is again logarithm of n. So we are performing the insertion n times, so the total time complexity will be n times log n. So this will be the time complexity of creating a binary search tree of n elements. Now there is a problem with this. Let's say that the elements that we are inserting are sorted, let's say 2, 6, 8, 12, 15, 18 and 20. So we'll first insert 2. 2 will become the root node, because currently we don't have any nodes in our tree. 6 will go towards the right side of 2. Then comes the turn of 8. 8 will again go to the right subtree of 2, which after comparing to 6, it will go to the right subtree of 6. So 8 will come here, 15 will come here, 18 will come here, and 20 will come here. Now, do you see a problem here? Instead of logarithmic time, it becomes linear time to search in this array, because it basically becomes a linear structure. As you can see, it's a line. It's just that these are connected like this in form of binary search tree. But again, the lookup operations in this will be linear search, linear time. The same case would be if we were to insert, if we were to create a binary search tree from an element, from a list of elements which were sorted in descending order. So let's say 7, 5, 4, 3, 2. So it would go like 7, the left 5 will come to the left of 7, then 4 will come here, 3 will come here, 2 will come here. Now this is a problem again. So there is a different kind of binary search tree that is called AVL tree that can help us get rid of this problem. AVL tree has some concepts which I don't think will be good to cover in this video. So in the next video, we are going to have a look at the theory of AVL trees. But before that, I think we should have a look at the coding part, how to represent or how to do operations on binary search tree, how to construct a binary search tree. We'll have a look at that using code. So the language that I'll be using is C#, but it should not be difficult for you to follow along if you are familiar with any other language. So the next video will be on the on realizing the binary search tree using C#. And the next video then will be the theory of AVL, and after this, the video that I'm going to make, we are going to have a look at the code of AVL tree. That's all for this video. I hope you liked it. If you did, please like, share, subscribe. Thank you.